My videos are dedicated to my beloved students so that they can learn physics through animation by relating physics to real life experiences. Let us make learning physics a fun. Please enjoy it. So today we are going to discuss Doppler's effect. So to introduce the topic, let us see this video. When a train whistling arrives a station and passes by you, what type of sound is heard? Please listen carefully. So this change in frequency of the sound, that is pitch of the sound, when a train is approaching you, then the pitch is higher. Pitch means आवाज जो है वो आपको तीखी सुनाई देगी. And when the train passes by you, that is when train is moving away from you, the pitch of the sound decreases. This change is called Doppler's effect. So let us analyze. Sound, as you know, is a longitudinal wave comprising of longitudinal wave, that is compressions and rarefactions. But in the present topic we will represent crests, which would mean compressions, and troughs would represent the rarefactions. So let us see what happens when a source is stationary and when the source is moving, the nature of the waves emitted by it. So when a stationary source is present, the waves emitted are equally spaced in both the directions, whether a person is stationary here or a person is stationary here. He would receive equal number of waves in both the cases. But if the source is moving, you can see the person on right hand side would receive smaller wavelengths, means more waves per second, whereas a person on the left hand side, as shown by the pointer, the waves received are rarer, that is lesser number of waves are received per second. So a person on this side from which the source is moving away would have lesser number of waves per second, that is lesser frequency, or we can call lesser pitch. Same phenomenon happens in case of sonic boom, in which the speed of the source is equal to speed of the sound. In this case, waves club together and a huge amount of energy is given towards the ground by the supersonic planes, which may shatter your window panes. So let us analyze it in another way. If source is at rest and the observer is also at rest, the waves are equally spaced in both the directions. So whether you can see in front of the source, the distance between the waves are same, and at the rear side also the distances are equal. But what if the source is in motion? So frequency heard is equal to frequency of the source, Fn. So if the source is moving forward, watch carefully, the first wave is given at the location as shown. When the source moves ahead, the second wave is emitted at a different point, third at next point, and so on. So you can see the waves are clubbing together when the listener is standing in front of the source approaching. What happens if the source is receding away? In this case, the waves on front of the source get clubbed together, but at the rear side they get more spaced, that is the listener would experience lesser waves per second. that is frequency hertz would be lesser. So let us analyze it mathematically. So if source is approaching or receding away, listener may also approach or listener may recede away. There is a change in frequency or pitch of the sound due to the relative motion. This phenomenon is called Doppler effect. I think definition is clear now. We'll discuss the effect in three different situations. First, when source is stationary and observer is approaching the source. So this is source. Say source is emitting n waves per second, that is frequency of the source is n, and v stands for velocity of sound in air. So the source is giving out n waves per second. Let us take this distance. Let us take this distance covered by the wave in 1 second. This distance should be velocity of sound v in air and into time equal to 1 second. So this complete length in which these n waves are enclosed, it is equal to velocity of the sound. This is an observer O. If source is stationary, observer is stationary, in next 1 second these n waves would be able to cross the listener in 1 second. Of course, the source would emit another n waves which would fill the space between observer and the source. Let me remind again, distance between source and observer is equal to velocity of sound into 1 second, that is v meter. So in a distance v meter there are n waves enclosed. Now let the observer starts moving towards the source. In this case, during 1 second, the observer would also be able to cover some distance, which is equal to velocity of observer VO into time 1 second. So observer covers distance VO meter in 1 second. So if the observer keeps stationary, then he hears only n waves per second. But in the second case, what is seen, observer has also moved through some distance. So this distance covered by the observer is in 1 second. So observer is able to hear these many waves more in 1 second. So let us find these number of waves, and that number would be added to original number n, which gives the new frequency heard by the observer. So let us find how many waves are there in distance VO meter covered by the observer in 1 second. For that you can apply unitary method. Number of waves in V meter are n. In 1 meter